First of all, this is my first time at Øredev, so thank you very much to the committee for inviting me. I'm really pleased to be here. I've heard great things about the conference over the years. I've just never managed to get here myself, so it's a pleasure to be here today. So I'm going to be talking today about this. If I turn this on, that will help. So I'm going to be talking about flow, microservices, and scale. Now, you might think I'm going to be talking about flow of work. I'm sort of going to be talking about that. But I'll be talking a lot about blood flow and circulatory systems. It's a bit strange, isn't it? I will be talking a bit about microservices, but what I've come to think of as the underlying physics of microservices. And I'll be talking about scale, but not scale in the sense of how to do 750,000 transactions per day, but scale in the sense of how companies scale, how software systems scale, how biological organisms scale. So I hope you find it interesting. It's, I think, the underpinnings of a lot of what we heard about this morning from Michael Feathers in his keynote. And also, if you're in Alan Kelly's talk earlier, about the no project movement. I think it underlies a lot of the reasons why we've moved away from projects. So that's what I'm going to be talking about. And I'm going to break the talk up into a number of parts. Don't move too far away from the laptop is the moral of that story. And those parts are going to be corporate metabolism. So why does everything slow down as we get bigger? So does anyone here work for a company that as it grows, things get faster? Can you put your hand up? If you work for a company where things get faster as you get bigger, for those in the front, there are 0 hands up in the audience. Yeah, and I think there's an underlying reason for that, and we'll cover that. The next thing is, how can we identify the signs of corporate aging? So as companies get bigger, get older, they tend to slow down. Why is that, and can we identify leading indicators that that is happening and act to stop it? The next thing is corporate mortality. So it's, I think, a little known fact, but the half-life of a listed company on the exchanges is about 10.5 years. So in about 10.5 years, 50% of companies on any given exchange will drop off. Companies die all the time. They go out of business, they go into administration, they get taken over, they get acquired. Why is that? And so as not to completely depress you, I'm going to finish off with the alchemist's stone. So given all this stuff that I'll be talking about, are there things that we can do to avoid slowing down money than God? And that comes with a downside, which I'll tell you about at the end. But that's essentially this 45 minutes. But first I'm going to ask a question, which you can consider throughout the rest of this, and that's how wide, given that Godzilla is about 115 meters tall, the latest incarnation, how wide would Godzilla's legs need to be? What's the diameter of Godzilla's legs for him to be 110 meters tall. And you might want to bear in mind what Michael Feathers was saying about Galileo's law, so that volume and area, as something grows, volume scales by the cube and area scales by the square. Or is it the other way around? I can never remember. Right, so think about that. So I'm going to quote myself here. So about 5 years ago, myself and Martin Fowler wrote what's sort of become to be the original definition of microservices. And we said, whilst we cannot say there's a formal definition, we can attempt to describe the characteristics that make up this architectural style. And it's these. So componentization via services, business capabilities, decentralized data management, products not projects, etc., etc. And the interesting thing about these characteristics is they all point in a particular direction. They all point to making these small things that are decoupled, that are cohesive around team boundaries. So organized around business capabilities, taking big problems, breaking them up into smaller problems. So my background originally was in physics. I was a terrible physicist. I'm not quite diligent, well, I'm not smart enough, frankly, to be a theoretical physicist, and I don't have the attention to detail to be a good experimental physicist, but nonetheless, that's how I see myself, when I look in. And so as a sort of pretend physicist, this is Melvin Conway. He actually exists, he's not a myth. Melvin Conway, all 82 years of Melvin Conway. And one of the interesting things about this workshop was we had an open space one afternoon, and we were all talking about the uses to which we'd put Conway's law over the years. Adrian was talking about Netflix and how in Netflix they cite the teams according to Conway's law. So you have your UI teams at one end of the building, then you're going to have your platform API teams next to them, because the UI teams only need to talk to the platform API, right? And then you've got the service teams, and then as you go along through the building, the infrastructure teams. Melvin Conway, as you can imagine, he's like, I wrote this in 1968, and like Netflix is doing this now. This is crazy. There were other stories that came out about organizing teams, and Mel was sort of shaking his head, like, I just can't believe that this is happening. But something else that came out of this workshop was a comment about this idea of organizations and slowing down. So another quote we had earlier, which was the mythical Man Month quote. Adding manpower to a late software project makes it later. But someone at this event said something really strange. And they said this. Someone from Amazon, can't mention their name, they said, the bigger we get, the easier it gets to get bigger. The more teams we add, the easier it is to add more teams. The more money we make, the easier it is to make more money. In fact, they went on to say, the only limit on our scaling is the number of people who can write code that we can hire. Now, does that sound like any company anyone in the room has worked at, unless you're at Amazon? One person at the back, for those in the front. So I was intrigued by this, and I went away and had a look, and a warning, pseudographs, this is not statistically significant set of data points, but nonetheless, and this is a graph that shows Amazon, the number of employees working for Amazon, and the amount of money they're making over time, revenue, specifically for AWS revenue. And what you can see in this graph, it's normalized, it's sort of log, but what you can see is this exponent, if you see x to the power 1.1515 up there, that exponent being greater than 1 means that they are scaling super exponentially. So as they double in size, they more than double the amount of money they're making. And that's pretty extraordinary. And so the rest of the talk really is about why. Why might that be? But seeing as it's lunch, or post-lunch, I thought I'd wake you all up with a brief and almost certainly incomplete introduction to nonlinear dynamics and complex adaptive system theory. So I hope that's all right for everyone. Good. Okay, fine. So this is the history of complex adaptive systems and nonlinear dynamics goes back to just after the birth of chaos theory, when an institute was set up, which I'll come on to, the Santa Fe Institute, to study this new science, if you like, of complexity science. At the same time, at Los Alamos, there was a nonlinear dynamics group, and they sort of smashed their heads together and started working on some really interesting problems, which I'll come on to. But first, a question. What do mice and elephants have in common? Anyone? Bueller? The fun thing is that mice and elephants and us have the same blood pressure, as does Godzilla, if it existed. All mammals roughly have the same blood pressure. Isn't that scary? Weird. Why would that be? Also, all mammals roughly have the same number of heartbeats in their lifetime, about 1.5 billion heartbeats. All of them. and the same blood pressure. So what varies? How can all mammals have the same number of heartbeats and the same blood pressure? Well, what varies is the animal's metabolic rate, the rate at which they consume calories. So your heart rate as you get bigger massively slows down. Time to you slows down. When you see a little mouse scurrying about, they're looking up at us and they're seeing these things moving with glacial pace because we are much slower creatures. Just by being bigger. I'll come on to that in a sec. What this graph actually shows is the scaling law for metabolic rate in mammals. So metabolic rate in mammals follows a scaling law with an exponent of 3/4. So that's under 1. If you heard me talking about Amazon above 1, this is under 1. So as you double the size of an animal, it needs only 3/4 of the calories in order to survive. You'd think you'd need double the amount of calories, right? Because you've got double the amount of stuff in you. You know, as you go from a mouse to something twice as big as a mouse, whatever that is, rat, I don't know. You know, you've got twice the number of cells. So why is it that metabolic rate scales at 3/4? So as a mammal doubles in size, it needs only 75% of the calories. Similarly with newsagents and sort of mom and pop stores and supermarkets, giant companies. If you actually plug the data in from NASDAQ and other places, what happens is you double the size of a company, you also get this scaling law, this power law. And in general, this is too few data points, but in general, revenue increases 85% of what you'd expect. If you double the size of a company, you don't double the revenue you get 85%. Right. Another scaling law. Cities. What do Hamburg and Leipzig say have in common, or two cities that are roughly double in size to one another? Well, as you double the size of a city, infrastructure costs also only raise by 85%. You only have to spend 85% of the money on roads, petrol stations, restaurants, water pipes, electricity cables. This is one of the reasons that cities tend to grow. It's efficient. They exhibit economies of scale. Alan Kelly was talking about economies of scale earlier. And you see these laws everywhere, power laws, these scaling laws in nature, across all sorts of weird places, including the neuronal structure of our brains and all kinds of weird places. And Geoffrey West, who wrote this great book, Scale, which I can't recommend highly enough, he has this lovely quote. Just let you read that for a sec. So what he's trying to get at here is in physics, in science, when you see things across multiple different places and lots of different areas, and they're all exhibiting the same behaviors, it points to this idea of some underlying set of principles. As I mentioned, I should define my terms. So economies of scale, as you double the size of something, if you get linear scaling, you double the size of the other quantity. But for economies of scale, you get sublinear scaling, blah, blah, blah. So I mentioned Santa Fe Institute. The reason I got into or was interested in following their work is this book I read by Murray Gell-Mann, the inventor of the quark, or namer of the quark, Nobel Prize winner. And he started the Santa Fe Institute with a whole bunch of other people. And their mission really is to answer the question of why we see these regularities across different parts of science, across different areas, across companies and people and rats and elephants. That's really what they want to do. And they're doing it in a really interesting way. And I'm sure you're familiar with the old joke about the silos of scientific disciplines, where you've got the biologist saying, well, I study life, so therefore biology must be the most important science. And then you've got the chemist saying, well, biology is just applied chemistry, so we must be the most important. And you've got the physicist saying, well, you're just applied physics. And then you've got the mathematician all the way over here saying, what are you doing? It's all maths, right? I think there's a good cartoon that summarizes that from XKCD, if you've seen that, which is this one, Fields Arranged by Purity. What the Santa Fe Institute is trying to do is smash together lots of different disciplines in order to get diverse opinions to answer these questions, these very deep questions about why do these systems exhibit these behaviors. So it's not about these silos of science, it's about bringing lots of people together. Now, doesn't that sound familiar from an agile software development perspective? Wouldn't it be good if we had cross-disciplinary teams, we're all working together to solve the same problem? But science is fractured into all these disciplines and micro-disciplines, these silos and smaller silos. And so that's what the Santa Fe Institute was put together to do. And they came up with this idea of complex adaptive systems, or complexity science. And they define complex adaptive systems as having 4 properties. So self-similarity is the first one. So they're built up from similar parts. We are built up from cells, as are rats, as are dogs and elephants, as would be Godzilla, presumably. In cities, you have self-similar bits, the buildings, the people, the kind of pipes, self-similar bits. Self-organization. So the ability for a lung to form from all these individual cells, that are organs to take shape. They self-organize. Complexity, so meaning that the whole, when you put all this stuff together, I am not just the set of cells in my body, I'm more than that. I am conscious. And then emergent behavior. This is the 4th principle. So that essentially, when you look at the whole thing, you can't predict its behavior based on the sum of its parts. And software systems and software architectures also exhibit these properties, if you think about it. All right? They're built up from self-similar parts, whether that's classes, whether that's methods or functions or microservices. You get emergent behavior from them. As you add more of these things, as they get more complex, more behavior emerges over time. So these complex adaptive systems are everywhere. And over the last 20 or so years, they've settled, or rather, Geoffrey West in his research has shown empirically that 3 principles can explain all of those power laws that I just showed you a minute ago around metabolic rate, software architecture, city scaling. What was the other one? Companies. Are you paying attention? Come on. And it's interesting because these principles are kind of similar to some of the things that Mike was saying earlier. So the first thing is this idea of space-filling fractal networks. I've shown you a hierarchical version of this. There are other types. But these sort of hierarchical networks are the first of these characteristics, first of these principles. The second is the new word I'm going to use for people on teams, software developers. Oh, God. I've gone back. So invariant terminating units, that's our new name for software developers, right? So invariant terminating units in us, and in mammals are cells. In organizations, they're people doing work. In cities, they are people and houses. And the third thing you need is optimization. For life, that's evolution, millions of years of optimization. In companies and cities, it's market forces, generally. And just with these 3 simple principles, you can explain all of those power laws. And I'll explain that in a minute. So the first thing is this idea of complexity science. Complex adaptive systems are absolutely everywhere. Everything you look at, more or less, is a complex adaptive system. And these interesting patterns that we see in nature can all be explained by these 3 simple principles of space-filling fractal networks, hierarchies, like our circulatory system, like the road networks in cities, like the flow of information in companies. And these properties scale as a power law with an exponent of less than 1. So all of these things, they can explain these power laws where you double the size of something and you don't get double the amount of stuff out. So basically what we're saying is for mammals, a mouse and an elephant are exactly the same thing. They're just scaled up versions of one another, which is bizarre. Okay, so on to this bit about corporate metabolism. That was the sidebar done. Why do metabolic rates slow as size increases? Basically, your heart beats much, much slower than a mouse's does, and an elephant's heart beats much, much slower than ours does. Consequently, they live at a slower rate. Their cells suffer less damage the bigger you get. So an elephant rarely suffers from cancer, for example. Blue whales hardly ever get cancer because their cells are operating at such a lower metabolic rate. And that's really what this graph is showing. Elephants are roughly 10,000 times heavier than rats, but their metabolic rates are only 1,000 times larger, despite having roughly 10,000 times as many cells to support. Consequently, decreasing the rates of cellular damage and so on. It's quite interesting why, and it's to do with the way blood flows in mammals, or in animals in general. The same for birds. So basically, we've got this hierarchy of blood vessels in us. Right? Starts at the heart, then you go into the aorta, and then after the aorta, it splits into a number of other arteries and splits and splits and splits. Until eventually you get to capillaries, which are the things that sit next to the cells, and you get calorific diffusion across the boundary of the capillary wall and the cells, and that's how we stay alive. And here's a fun thing about the optimization part of this. As you split as an artery splits, the two arteries it splits into, the vessels it splits into, have exactly the same cross-sectional area as the original artery. Exactly the same. So basically evolution has optimized this. And can you imagine why that might be? What would happen if you had a pipe, and then you had two smaller pipes, but they were slightly smaller overall than the original pipe? What would happen to fluid pumping through it? Actually, it would do the opposite thing. It would slow down, because you get interference at the boundary. At the split, you would get interference. So blood, in the case of us, or fluid in the case of oil or water pipes, would bounce off that boundary and force itself back up, essentially, the original pipe. You get back pressure. So evolution has optimized that out of humans and mammals, because back pressure on the heart, that doesn't sound particularly great, right? That's not a cool thing. That's not what we want, ideally. We don't want our heart to be beating against itself. And this is why build-up of plaque in arteries is such a bad thing, because we no longer have this exact split between one and these other two. We have a narrowing which causes this back pressure, puts more pressure on the heart. So as our circulatory systems split into more and more bits, they're going to eventually end up in capillaries feeding our cells. And the only difference between us and an elephant is essentially the depth of the circulatory system, the depth of the hierarchical network of blood vessels. But apart from that, we're exactly the same. One's got a trunk, I've got a nose, but we're exactly the same, pretty much. Another fun thing is that, can anyone guess the smallest size for a mammal? I'm not sure anyone's going to be able to do this. It's about the size of my thumb, that bit there, up to the first knuckle. I think it's called the Etruscan shrew. It's the smallest mammal in the world. And the reason you can't get smaller than that is because in the circulatory system, you have to have at least some pumping. There has to be at least one layer of artery before you hit the capillaries. You have to have at least some AC voltage, if you like, before converting to DC continuous flow. Because that's what happens when blood hits the capillaries. The viscosity of blood is such that it can't, that it has to flow continuously because it can't overcome the diameter of the tension caused by the capillary walls. But essentially, they're the same size. The bottom ones, the invariant terminating units, are the same size, and the smallest thing and the biggest thing differ only in the depth of the circulatory system. So, bigger animals are more efficient because they take advantage of this impedance matching in the circulatory system built in by evolutionary feedback over hundreds of millions of years. But there's a fun thing that happens in companies. You can get the data, or you can predict essentially data on companies' growth based on depth of hierarchy and age. So as companies get older, they get more efficient. driven by market forces, 85% efficiency you get out, right? So you don't make twice as much money, you make 85%. And they also slow down, as we talked about at the start. And why is that? It's exactly the same reason that big animals are slower than smaller animals. Stuff just gets slower based on depth of hierarchy, based on the depth of a hierarchical network within a company. Like, actually, there's maths to show this. If you're in an organization with a very deep hierarchy, you will just be slower than one without that hierarchy. It's literally maths. And do you remember the mathematician over there, right? It's maths. And you can think about this, right, as how work is flowing through these networks in these value streams. So if you think of a value stream map as one flow of work through an organization, and if you look at a value stream map for a big company, this is a company I was working for a little while ago. There's quite a lot going on in this value stream map. Every single little post-it note is essentially a handover between different groups, between different teams. It's change request boards, it's architects doing reviews, it's et cetera, et cetera, et cetera. Actually, there's a little bit, if you can see there's this circle a bit, that was two different types of enterprise data architect, each updating their own model, giving their model to the other enterprise data architect who would update their own model. They existed in a world which had no effect at all on the rest of the organization. It's quite impressive. When you see these sorts of value stream maps, what you're essentially seeing is this really deep hierarchy, right, of a very large, slow organization, and old, generally. What you also see here are queues. These little symbols represent queues of work in the system. And when we put queues in, what we're essentially doing is deliberately blocking corporate arteries. We're just causing plaque to form in the flow of information through the corporate information system, basically. We're deliberately giving ourselves heart attacks by adding all these queues in. I think there's a famous quote from Don Reinertsen from Principles of Product Development Flow around the effects of queues, which are all these things. But fundamentally what we're doing is we're blocking the flow of work. We're impedance mismatching, essentially, and putting back pressure up the corporate system, up the corporate hierarchy. So corporate metabolism, as we scale, they add more and more process and more layers of hierarchy. And as you increase the depth of this network, things slow down. It's literally just maths. But we also don't do things that could help us. We deliberately block our corporate arteries as well. So how do we identify whether we are slowing down? So this brings me on to another set of research that's come out in the last 5 years, summarized in the book Accelerate. This is one of the greatest, I think, books about what we do, because it's a bunch of data that points to the techniques, the practices that we can use to become high-performing organizations, not IT organizations, organizations. Here's a fun fact from that research. Change request boards predict low performance. If you have a change request board, it predicts you're in the low-performing group in the research. That's fun. Another one, if you outsource by job function, so if you outsource all of testing, that's correlated with low performance as well, which is a bit scary. But given what I just said, you can kind of understand why, right? It's kind of a bit like the outsourcing by job function is a bit like having to go on dialysis or something, right? You've taken your kidneys outside your body and someone else is having to deal with it. And putting change request boards in, that's literally, again, deliberately blocking the flow of work. It's deliberately putting back pressure, starving the system downstream of nutrients, of oxygen. But the good thing is this research points to these 4 key metrics that you can use to monitor organizational health, essentially. So mean time to recovery, cycle time, change failure rate, and number of deploys per unit time. These are leading indicators of corporate health. In the same way that your blood pressure and your heart rate and your body temperature are leading indicators of your own health. So we can actually use these as leading indicators to work out whether we're getting better or worse. Most organizations don't measure these though, but I would recommend doing so if you can. And you can do this using automation generally. So as I say, you can use these leading indicators, 4 key metrics, to monitor your health. And it's the equivalent of going to your doctor. But it should be pointed out, the hierarchy implies 85% revenue. It implies economy of scale. You can only improve your organization up to the limit imposed by the hierarchy that you already have. Now, corporate mortality. I mentioned that it's about 10.5 years is the half-life of an organization. And this is still an ongoing area of research, but it looks as if the reasons are around things like research and development spend and becoming much more risk averse as an organization gets older. So R&D spend as a proportion of revenue massively decreases the older an organization gets. And that appears to be correlated with organizations actually dying. And you add more processes, you add more constraints to manage the hierarchy. And these hierarchies grow and grow and grow and grow and grow and grow. So to conclude the corporate mortality section, when we organize hierarchically, the data suggests that we get economies of scale. So this is both good and bad. So it's good in the sense that we don't need to spend as much money on things like network cables, right, or building costs. We get economies of scale for that. But we also get this economies of scale for revenue. So we can only make about 85% of the revenue as we double the size of a company, purely based on the maths of hierarchical space-filling networks, invariant terminating units, people doing the work, and market forces. So essentially what we're doing is as we're growing, we're decreasing the corporate metabolic rate. And unfortunately, this means, like we die, the same effects mean that, or imply that, in general, companies die too. So that's kind of depressing. So who works in a company that doesn't have a hierarchy? Who works in a company whose hierarchy doesn't grow and grow and grow? Yeah. But there is something we can do about this, which is good. Because there's another thing that happens. There's another effect we observe in nature, and this is something called returns to scale. So if you remember, I said economies of scale is where you get this graph and you grow sublinearly. So as you double the size, you get less than double out. Superlinear growth implies the opposite. As you double in size, you get more than double something out. That's the definition of returns to scale. And the cool thing is there is an example out there in the world of things that do both of these, and it's cities. So cities exhibit economies of scale for infrastructure. So you only need 85% of the roads, for example. But for socioeconomic effects, you actually get returns to scale. So as you double the size of a city, you get more than double the number of patents, so innovation, more than doubles. All right. The wages more than double as you double the size of a city in general. And the number of professionals in a particular area more than double. But also crime, disease, pollution more than doubles. So for socioeconomic effects, you get returns to scale. And typically this exponent, as I say, is 1.15. Oh, walking speeds, that's right. You know this whole thing about you go to London or you go to, I don't know, Copenhagen, everyone's walking really fast. They actually are. There's now data to show that as you double the size of a conurbation, people's walking speeds do increase with an exponent of 1.10. People do actually live faster in bigger cities, which is weird. So why is this? Well, it turns out social networks are the key. Social networks are the drivers of superlinear growth. So these numbers I've got up here slightly disagree with the number we heard this morning of 100 for Dunbar's number. So Dunbar has a range of these numbers describing different types of interaction between humans. So 5 is essentially your very, very close family and friends. Very, very close family. And it's a bit awkward because I've got 6 people in my family. I've got 4 children, me and my wife. So that means technically I do love one of them less. I'm not sure which one. Maybe it changes over time. I don't know. It's a bit awkward. Then you get this scaling by factors of 3, so 15 people is the next number. These are this sort of very, very close friends, very nuclear family. Then 50, then 150, and then 500. And these are to do with our neuronal structure of our brain, how many connections we can actually hold. So why should that impact superlinear growth? Or should have an impact and cause superlinear growth? Well, it's to do with this thing called the multiplicative effect of association. So as you go from a small village, where your Dunbar's number of 500 people, all the connections that you can keep in your brain, that's the entire village. You don't get to choose who to associate with. But if you go to a city of 13 million, you get to choose who those 500 people are. If you're a lawyer, you get to hang out with other lawyers, apparently. If you're an accountant, you get to hang out with other accountants. If you're software developers, you get to hang out with other software developers. And that effect of having these connections with people who are like you, who share your interests, share your sort of intellectual curiosity, causes this superlinear scaling of innovation, of wages, of number of professionals, and these things. But if you remember, I said at the start, well, towards the start, there were these 3 principles. And one of the principles is space-filling fractal networks. Well, the fun thing is that space-filling fractal networks come in more than one form. And so you get hierarchies, which cause economies of scale and things to slow down, and you get fractal small world networks, like social networks, which cause things to speed up. So how do you take advantage of growth in small world networks? How do you build organizations that are using these facts in order to scale effectively? So to summarize that bit, as cities grow, they get economies of scale for infrastructure, but they get returns to scale for socioeconomic things, good stuff and bad stuff. So innovation, patents, but also crime. And the other thing is cities don't tend to die very often anyway. They tend to be very stable and long-lasting, as opposed to companies or biological life forms. So you get 115% more stuff for 85% of the cost. This is why they are such attractors. This is why they suck individuals in from all over the place. Essentially, what cities act as is a sort of reactor. They suck people in from outside, churn them all up in some big reaction, and the reaction products, if you like a star produces light, cities produce ideas and innovation and crime and pollution at an ever more efficient rate. Pretty cool. So if you could organize like that, surely, as you double in size, you've saved money on infrastructure, you more than double the amount of revenue. Well, I would argue that actually this is what many of the organizations we hear about are designing themselves to do. So the Spotify model is an attempt to create small world networks within a company. Really, small teams working on small product lines, right, interacting with one another. Conway's Law again. ThoughtWorks, the company I work for, we've scaled according to this. So we're about 7,000 people now, but we're in about, 20 offices, something like that. More like 35 offices. As we reach about 200 people, we create a new office. We don't scale our offices much bigger than Dunbar's numbers. And that's deliberately so. And we've been able to grow pretty successfully. It's about 20% year on year for revenue. Valve. So if you remember the leak from Valve's employee handbook some years ago, they actually had a small world network in it. They said, this is how we're going to grow the company. We're going to grow by creating these small world fractal networks, because that will be a driver for superlinear growth. And then going back to the start, when I was talking about Amazon and this claim that as we get bigger, it's easier to get bigger. As we double in size, it becomes easier to grow. So how did Amazon do this? Well, I think you can trace this back to about 2004, where there was a set of constraints imposed on how they structured themselves and the software they're building. A set of principles and a set of constraints. And they are things like the two pizza teams that everyone knows about, but then teams must communicate via interfaces, well understood, externalizable interfaces. Interfaces that we can then go on and sell, should that become necessary. And then two pizza teams. So this set of constraints is essentially deliberately designed to create a small world fractal network within the organization. And you know the old saying, it's not paranoia if they are out to get you. You've probably come across that before. Well, it turns out that Jeff Bezos is a patron of the Santa Fe Institute. He's actually funding a lot of this research. He knows all this stuff, and he's done it deliberately. The rest of us have sort of been in the dark a bit about this. And these constraints have led to this superlinear growth effect. So as most companies get bigger, it gets harder to get bigger, and that's literally because of the hierarchies involved. It's maths, fundamentally. Metabolic rate slows down based on the depth of your hierarchy. But as Amazon gets bigger, it gets easier for them to get bigger. I'll go back to that quote. There's this sort of underlying framework here for why we should organize in a particular way. I wouldn't say grand unified theory of organizational design and software architecture, but it's along those lines. You get good stuff if you organize in a particular way, and bad stuff if you don't. And then going back to microservices, a lot of these characteristics are essentially, we're searching the solution space for this underlying set of core principles. If you do this stuff, this is the recipe. But the underlying reason are these core principles. So I'm supposed to give you something to take away. So if you're going to make a move towards this stuff, start where you are, get the basics under control, track organizational health, work sustainably to improve the 4 key metrics. Don't skimp on innovation. It's literally the lifeblood of your company. But then this idea of social networks and socially connected networks, that's the thing that causes superlinear growth to occur. So sublinear growth, they're caused by hierarchy. So can you experiment with these small world networks in your own organization? What would that look like? And think externalities. When building capabilities, think, could we sell this to someone else in the future? That was the effect of one of Jeff Bezos' constraints. And finally, the answer to the question, how wide do Godzilla's legs need to be? Has anyone got an answer for me? 10 meters. 10 meters. That's not a bad guess. So based on about 115 meters tall, I didn't do the calculations, this was Jeffrey West, needs to be about 60 foot, so that's about 20 meters, each leg about 20 foot in diameter. The heart would weigh about 100 tons. It's quite cool. It would need to pump about 2 million liters of blood around Godzilla's body, and it would only beat about twice a minute in order to retain blood pressure and all that kind of stuff. It would also live for about 1,000 years. Final quote, Stephen Hawking, I think the next century will be the century of complexity. There is no limit to the complexity that we can build using these basic laws. You probably want to read these books. They're awesome. And finally, there's other references for the original research. So I'll leave it there because I'm about 30 seconds over. Thanks very much for your time.